All right, I want to start this idea of inverse transformations off with kind of two motivating questions. So, say we have a matrix representation for a transformation going from V to W that is injective. So, what we know about being injective is that the dimension of the domain has to be less than or equal to the dimension of the codomain. And so remember that when we have a matrix form of linear transformation, it's going from Rn, where here we have the number of columns, to Rm, where we have the number of rows. And so we talked about in the last video how if we have the matrix form of transformation, the number of columns is going to be the dimension of the domain, and the number of rows is going to be the dimension of the codomain. So that means if we have a injective matrix transformation, then we have something where the number of rows has to be greater or equal to the number of columns. Now for an onto transformation, we have the exact opposite. We need the dimension of the domain to be greater than or equal to the dimension of the codomain. So that means if we have a matrix that's going to represent a transformation that's onto, the number of rows of the matrix has to be less than or equal to the number of columns. All right, so we've actually talked about an application of needing these matrix forms and these properties with our radiography and tomography stuff. But our idea is that we want to know, with the tomography portion, what the object was that produced the transformation. So suppose we have a transformation going from Rn to Rm, and it's represented by a matrix. Suppose we also know that the vector is obtained by transforming some v, but we don't know what the vector was that gave us that transformation. Essentially, we want to find a way to work backwards and tell us what that vector was. So our way of doing that is going to be by constructing an inverse matrix when our dimensions are the same, so when m equals n. So recall that an inverse function for a transformation is one who, when you take the transformation and its inverse with some input, you get back that input. You might have learned this in calculus. However, it can be difficult to construct an inverse function, and sometimes the inverse isn't even going to exist. But when we have something that is a bijective transformation, we can find an inverse transformation that goes and takes our codomain as input and spits out vectors from our original domain. And sometimes it's difficult for us to construct this inverse linear transformation, but if we have a matrix form of the transformation, it's really not that difficult. So we're going to let our matrix be an n by n square matrix. So the dimension of the domain and the dimension of the codomain, they need to be the same. The inverse of that matrix, which we're going to call M inverse, is, we're going to say it has an inverse if and only if there's a matrix such that when you take the matrix and multiply on the right by that inverse, or if you multiply on the left by that same matrix, you get the n by n identity matrix. So we've mentioned the identity matrix before. So I2 is something along the lines of 1, 0, 0, 1. I3 would be 1s along the main diagonal, 0s elsewhere. And you can kind of imagine for bigger and bigger identity matrices, it has the same number of rows and columns, and the defining feature is 1s along the main diagonal and 0s everywhere else. Now notice that normally matrix multiplication does not commute. You can't just switch the order, but for matrices that have their inverse, the matrix does commute with the inverse, and you'll get the identity matrix of the proper size either way. So here's our plan for finding the inverse of a matrix, and it's actually pretty easy for us to do, knowing what we know. If we want to find a inverse for a matrix A, what we'll do is we'll take the matrix A, we'll augment it with the identity matrix of the proper size, and then we'll get the reduced row echelon form of that matrix, and then the identity will show up on the left side of the augment, and A inverse will show up on the right side of the augment. So in order to find it in octave, you can either type inverse A, or I believe inv A works as well. I don't know if this has been updated or not. At one point it didn't work. I think it did, and then I think it didn't for a while, so double check. One of these two should work for finding an inverse. So what we're going to do is we're going to try to find an inverse for this particular matrix. So we'll start off by taking our matrix augmented with the proper size identity matrix. In this case, I2. So we'll have 1, 3, 0, 1 augmented with 1, 0, 0, 1. And so what we want to do is we want to get the reduced row echelon form. And so in order to do this, all we'll have to do is we'll need to take row 1 and make it row 1 minus 3 row 2. And so this will give us the matrix 1, 0, 1, negative 3, 0, 1, 0, 1. So that means, since we have the identity matrix over here, and we'll have M inverse over here. So M inverse is going to be 1, negative 3, 0, 1. And just in case you wanted to check, what you can do is you can take the matrix 1, 3, 0, 1 times its inverse of 1, negative 3, 0, 1. And when you do this, what'll happen is you will get the first row, first column entry will be 1 plus 0, which is 1. The next entry in the first row, but the second column will be negative 3 plus 3, which is 0. Second row, first column will be 0 plus 0. And the second row, second column will be 0 plus 1, which is 1. So indeed, you do get back the identity matrix, so it does work. So if we get the identity matrix over here, we have an inverse. Otherwise, we don't have an inverse for our matrix. So if we try to find the inverse of this matrix, what will happen is we'll start off with our augmented form, and we'll get the reduced row echelon form, and what we'll notice is that we don't get the identity matrix over here. What this means is that there's no inverse for this matrix. So that's one way to tell. Another thing is that we're not going to have an inverse for something that's not a square matrix. So if you don't have a square matrix, you can't get an inverse of it. Now, a little bit of a fun lemma, fun trick that you can show your friends at the lunch table when eventually there are lunch tables again, is if you want to find the matrix, or the inverse of a 2 by 2 matrix, it'll be found by switching the top left and bottom right corners of the matrix, flipping the signs on the top right and bottom left corners, and dividing by AD minus BC. So top left times the bottom right minus the top right times the bottom left. So for our particular matrix, notice that we started with 1, 3, 0, 1. So M inverse is actually going to be found by switching the position of these two. So 1 and 1. Switching the signs on these, so negative 0, which is 0, and negative 3. And then multiplying by 1 over A times D, which is 1, minus B times C from here, which is 0. And so it gets our inverse of 1, negative 3, 0, 1. This trick only works for 2 by 2 matrices, so don't read too much into it and try to figure out how it works for something bigger. Speaking of something bigger, let's look at this matrix. So we're going to start off here, And again, all we need to do is we need to take our matrix and augment the identity matrix. And then what we'll do is we'll do a series of row operations until we get the identity matrix on the other side. So now we have I3 over here. And this portion is going to be M inverse. So notice if you take this matrix times this matrix we just found, you get back the identity. So that means that this will be our inverse. All right, a few nice properties of inverses. First is that if a matrix is invertible, then so is the inverse. And the inverse of the inverse is the original matrix again. If we have a matrix that's invertible, then its transpose is also invertible, and the inverse of the transpose is our own inverse transposed. And last but not least, if we have two matrices A and B that are invertible, then A times B is also invertible, and the inverse of A times B is going to be B inverse times A inverse. Well, why is that? So there's a little bit of proof here for each of these properties. I want to focus on that last one because it's kind of the least intuitive. So if we have AB times what we're calling AB inverse, we're saying that's A times B inverse times A inverse. B times B inverse is going to be the identity. So we have A times the identity times A inverse. Anything times the identity is itself. So we really just have A times A inverse, which of course is the identity, which means that this was indeed the inverse we were looking for. All right, we got one more theorem, two more theorems. Next one's kind of a doozy. If A is an n by n invertible matrix, then for each B in the real numbers in Rn, the equation AX equals B has a unique solution of X equals A inverse B. So wait a minute, what does that mean? What that means is that if we have AX equals B as our equation, the thing we've been solving by getting the reduced row echelon form each time, all we really need to do is find A inverse, go ahead and multiply on left on both sides, and this gives us the identity matrix times X equals A inverse B. But as we just discussed, the identity matrix times anything is just itself. So we have X equals A inverse B. That's really neat. So that might raise a few questions. One question is, well, if all we had to do this entire time was find the inverse and multiply on both sides by that, what have we been doing all this reduced row echelon form stuff for? Well, first thing is that this only works for n by n invertible matrices. So first you need a square matrix, then it needs to be invertible. Second, the way we find our inverses is by doing reduced row echelon form, or getting things into reduced row echelon form anyway. So by the time we've done all that, we might as well have learned how to reduce row echelon form stuff. But in the event that you have an n by n invertible matrix, this is one way to do it. Now note that from a computational standpoint, this usually is not the most efficient thing to do. But if you had the inverse, you could use it to find what X was and figure out your solution. This last page of the notes is something called the invertible matrix theorem, and it ties together a lot of the properties of things that we've been looking at. So suppose we have an n by n square matrix. So we're saying that everything here is either going to be all true or all false at the same time. So first, if we say that our matrix is invertible, that's going to mean that we have n pivot positions. And what we mean by n pivot positions is that our rank for our matrix is going to be n. And because of the rank nullity theorem, what this tells us is that we have a nullity of 0. So this is from n by n matrix and rank nullity theorem. So if we have a nullity of 0, the null space of A is trivial, which means that the only way AX equals 0 is if X is 0. It also means that the columns form a linearly independent set, and the columns span Rn. Okay, well, that kind of all comes from the rank being n, which is great. If the nullity is 0, then the linear transformation represented by the matrix is injective. And if the rank is n, then the linear transformation represented by the matrix is surjective, because then the rank equals the dimension of the codomain, which is n. The equation AX equals B has a unique solution, which is great. We just talked about that. A transpose is invertible, again, one of our properties. And we have these matrices C and D, which happen to be A inverse most of the time, except in weird cases that are way outside of the scope of this class, where we have C times A equals the identity, and A times D equals the identity. So we have basically these inverse matrices that we can find on either side. So note that either all of these are true or all of these are false at the exact same time if you have a square matrix. Right? It's possible to have a square matrix that represents a transformation that is not injective. But if it's not injective, neither is it surjective if it's a square matrix. And if it's not injective or surjective, then we're going to get infinite solutions when we try to use it to solve an equation. And it's not going to have an inverse. And we're going to have a non-trivial null space, and we're not going to be able to get Rn, a basis for Rn with the columns,